Hello everyone. So let us begin. Now, in this one, we are going to continue about what we did in the last section, and integration and differentiation were almost done. So let me just write down the heading for you. So now we'll be seeing what integrations do we need, because in the last one we tried to do some of the stuffs from statistical analysis and Bayesian interference, and we did MLE, point estimation. We understood how to do the MLE, so I'll just do a recap on MLE first. The MLE is basically maximum likelihood estimator. Now we would like to understand that given a test statistic we would like to know that if this test statistics or the PDF can be maximized, right? So if you have, let's say, f of x1, x2, xn, and this is the joint PDF, and let us say it is also equipped with the parameter theta. This theta is what we call the stress statistic here, and we would like to maximize theta. So what we generally do is as follows. So let me give you an example. Now Now in exponential distribution, we do know that fxx is simply equals to lambda into e to the power minus lambda x, right? Now this accounts for the fact that we can have n random data sets from a random sample, and we can understand that this random sample basically is something we would like to maximize if a joint PDF is given. Now the joint PDF for x1, x2 and up to x10 would be The likelihood function is written as L of x colon theta, where theta is the parameter. And obviously this is basically the product of all the joint PDFs we have out there. So we can define it as follows. So this product definition gives you the joint PDF. Now so this would be the entire result. Now our goal is to do the following. Therefore, what we can do is right. Now obviously this is the function that needs to be maximized, and let us see what value of lambda would allow us to do so. So what we do is instead of the likelihood function, we rather maximize the log likelihood function, and since the log likelihood function is simply increasing, we get to see the results we want. So it basically works as follows. Now using the properties of log, we can distribute the multiplication into summations of logs. So now we need to maximize this, so we differentiate both sides with respect to lambda to get the following. Therefore, so the maximum likelihood estimator basically says that the value of lambda for which the probability will be maximized is basically 1 upon the sample mean, which is basically the answer. Now we understand that this can be done in separate ways, and the embedded videos here will also let you know about all the techniques you need to understand about derivatives and integration, and about exponential distribution and its MNEs. So we are trying to find out some problems, and before that we would need a few results which we try to prove. So result that we need to prove for this section is this: limit of x tends to infinity 1 plus 1 by x whole to the power x is equals to e. Okay, so basically what this means is this can also be rewritten in the form limit x tends to 0 1 plus x whole to the power 1 by x is also equals to e. So both of these limits are equivalent, and we would try to use this result in a few cases. So let us see how to actually achieve that. Now this one is a bit more challenging than previous ones, because we would start off with something we know as the binomial formula. So binomial expansion. Now what is a binomial expansion? So a plus b whole to the power n, this can be expanded when n is a natural number as follows. Like this. So using this we can also find out this expression right here, that 1 plus 1 by x whole to the power x expression, where we know that x is a real number, but for the time being we can actually find out something about it. Like this is also valid for rational numbers and real numbers, but just that we have not done that yet. But we can still use this to find like this, but it would be an infinite series because of the x here. It should be x ck into 1 is irrelevant, so 1 by x whole to the power k, right? Now the thing that is to be noted is this term here. If you just write it as a function of both k and x, it can be written as x ck into 1 by x to the power k, right? Now, how to define this binomial coefficient in terms of rational numbers or real numbers or even negative numbers? So there is a definition. It is same as the one that you define with natural numbers, but just that you do not do the factorial thing here, because factorial makes no sense, right? Because you cannot really find out 0.5 factorial because it doesn't go back to 1. Factorial means that you multiply the integers consecutively until you get 1. But in case of real numbers, in case of rational numbers, that's not how it makes sense. Okay, so what makes sense is this: xck can be written as x into x minus 1 into x minus 2 and all the way up to x minus k plus 1 divided by k factorial. This is the expression, and you have a x to the power k extra in the denominator, which gives us the expression for this. And we are literally trying to find the limit of this expression right here, right? So one of the x's can be cut off, obviously, and what we do get is this: x by x into x minus 1 by x into x minus 2 by x and all the way up to x minus k plus 1 by x. And then there is a 1 by k factorial. And now there are k terms, so I've divided all the k x's in as denominator to this one. So this gives us 1 minus 0 by x into 1 minus 1 by x and all the way up to 1 minus k minus 1 by x whole divided by k factorial, right? Which can be written in the product form as follows: summation r equals to 0 to k minus 1 1 minus r by x, and there is a 1 by k factorial outside, right? Now this definition gives us the notation for factorials, and it can be proved in later sections when we will be discussing about infinite series and infinite products, that this product right here is equal to 1 by k factorial when you put the limit, of course. So when you put the limit, this product is equal to 1 by k factorial into ek factorial, which gives you answer as e. But this product can be evaluated in multiple ways actually, because this product right here has an integral form as well as a differential form, and using the methods of Riemann integration, a lot of times infinite limits can be evaluated, which we shall learn when we get to the integration section, or maybe we can have a glimpse of what's happening, but for now this should work. So this is the basic proof. Now let us do some examples. Example 1: find the limit of sin x by x as x goes to infinity. So basically what we are asking to find is, we can denote the limit by L. So denote the limit by L, and L would be equal to limit x tends to infinity sine of x by x. Okay, now how do we do this? Now this cannot be done because obviously you remember a quite close one where x tends to 0 was given, and if x was going to 0 we knew that sin x by x approaches 1. But here the case is a bit different, and we can clearly see the denominator x, as x goes on to become larger and larger, the denominator becomes much larger, right? And the number should be decreasing by then, the limit value should decrease a lot. But doesn't sin x also increase? No, it doesn't, because we know that sin x for every real value of x lies in the closed interval -1 to 1 for all x belongs to real, right? So this is a property of sin x, that sin x is bounded. Then we can see that sin x is greater than equal to -1, then sin x by x should be greater than equal to -1 by x. Similarly, sin x is less than equals to 1, then sin x by x should be less than equals to 1 by x, right? It is evident that limit x tends to infinity 1 by x is equals to limit x tends to infinity -1 by x is equals to 0. So both the limits actually go to 0 irrespective of the sign, and also since we can bound the function sin x by x using this as we have done here, so we can basically write -1 by x less than equals to sin x by x less than equals to 1 by x, right? Now I'm going to quote a theorem here. It's called the sandwich theorem. It's called the sandwich theorem. It says that if fx, gx, hx are continuous functions, then if fx is less than equals to gx is less than equals to hx, and limit x tends to a fx equals to limit x tends to a hx, and both of them are equal to some alpha where alpha is a real number, then the sandwich theorem states that then limit of x tends to a g of x must also be alpha. So this is the sandwich theorem. That is, the function g of x has been sandwiched in between the functions fx and hx. Okay, so hx is the upper bound for the function, fx is the lower bound for the function, and it is given that the function fx and the function hx, both of them go to some real number alpha when x tends to the value a. So both sides of the limits in which the function gx is sandwiched goes to the same real number alpha, which means that the function in between must also go to alpha, otherwise the inequality would be violated. There is a whole proof for this, but we are not really going to do the proof right now because of the complications, because we need to know what is an epsilon delta definition of a limit. This is completely an analysis course, so I'm not going to quote analysis right now unless we need it when we go to the further chapters in probability. So using this we can see that since equals to 0, we can say that limit x tends to infinity sin x upon x must also be 0, since -1 by x less than equals to sin x by x less than equals to 1 by x. Since sin x by x is basically sandwiched between -1 by x and +1 by x. So that would actually solve this problem. So as I said, this is not like a regular problem, but problems like this would be very much evident. Okay, for the next problem I would need a footnote here, that is the footnote of a derivative of a function fx. So derivative of x f of x at x equals to a is defined as, I'll give you the formal definition of derivative for here, and we are going to revisit it when we start derivative, but for this problem this much information is sufficient to do the problem. So f dash a is basically equal to limit x tends to a f of x minus f of a by x minus a. So this basically is the definition of derivative. Okay, this limit, the value of this limit gives you the answer to f dash a. Now the problem, given f of a equals to 2, f dash a equals to 1, g of a equals to minus 1, g dash a equals to 2, then find limit x tends to a, g of x into f of a minus g of a into f of x divided by x minus a. So consider the problem. We are given that f and g are two functions which are first time at least once differentiable at the point a, and it is given that f of a is 2, g of a is minus 1, while f dash a, which means the derivative of the function at the point a of f is 1, while g dash a is 2, right? So g dash a is 2 doesn't mean that the derivative of g is 2, it rather means that the derivative of g at the point x equals to a equals to 2. So don't be confused with the definitions and the terminologies I'm using, because it's important that you understand them distinctively. Now limit x tends to a, g of x into f of a minus g of a into f of x. What we are going to do here is something like this. We are going to add and subtract ga fa. Minus g of a into f of x, and we are going to draw a line x minus a. Now why did we do that? Because we are going to separate this first two terms and this last two terms and write them as a separate limit. You will see why. Because we want to really find out how to evaluate this kind of problems using all the information given in the problem, and whatever we just learned a bit ago about the definition of a derivative, which you can see here, this would be handy here. So this becomes g of a into f of a divided by x minus a, plus another limit x tends to a, g of a into f of a minus g of a into f of x divided by x minus a, right? Now what we can do is we can take the constant common, which is f of a, from the numerator, and we can write this as f of a into limit x tends to a, g of x minus g of a by x minus a. Similarly, we can take minus ga common here, and we can write limit x tends to a, f of x minus f of a by x minus a. Now if you remember, this was the definition for the derivative of the function at point a, right? So f of a into g dash a minus g of a into f dashed a. This would complete the derivative section for this one. And now it's just a matter to put the value. So fa is 2 and ga is minus 1 and g prime a is 2. So first two terms are 2 into 2. So this gives us the value of 5. So this would actually solve this problem, but as I said, you would need this definition. So once you learn the derivative section, I do not think this would be any more required, but these are the basic things that you should know. Okay. So firstly, understand what is hypothesis testing. And in hypothesis testing, what we usually do is we try to understand what is the hypothesis, what is the null hypothesis. So there are two kinds of hypothesis. The null hypothesis is written as h naught, which is this, while the alternate hypothesis is written as h1. Okay, and what we can do is we can understand this from various examples, and we can understand that this kind of problems have a lot of ways to be acceptance. But obviously, first we are trying to understand how to handle this. So a null hypothesis is something which is given, and we would like to say some parts about it, some parts about the null hypothesis, where how we can handle, like let's say if the null hypothesis is theta greater than equal to 2, then the alternate hypothesis should be theta less than 2. So what happens is, if h naught belongs to the set A and h1 belongs to the set B, and if U is the universal set, then we must have A union B equals to U, while A intersection B equals to phi. This is what it should have, because the null and alternate hypotheses are basically reverses of each other, so they are complementary. Now, that being said, what we can now do is we can understand it from an example, and while also understand the various terms involved, like type 1 error, that we reject h naught when h naught is true. So type 1 error is defined as, when we define type 1 error as the event that we reject h naught when h naught is true, and we can find the probability of type 1 error. Right. So it basically is this. Now, one more thing is level of significance or significance level, which is usually denoted by alpha. So we set a significance levels beforehand for our test, and we say that if okay. So well, obviously this is what we call as the type 1 error. So probability of type 1 error given theta, if it is less than equals to alpha, which is significance level, and this usually gives us that the test is significant and we should proceed with it. But if the probability is greater than that, then there are other ways to test that. Similarly, there is a type 2 error. So this is called type 2 error, and it means that we are going to accept h naught when in reality h naught is not true, which is h naught is false. So this is also a type of error, and it is called basically type 2 error, where or we can also call it bit of theta. So there are various ways of doing that. So since it is usually denoted by beta, you can write beta of theta, where theta is the parameter of the test statistic. Now, so we are given this entire thing, and now we are going to understand each and every problem in a very similar way. So what we are going to do is we are going to do three more examples, and very typical and very nice examples actually. And what happens is, when we do these examples, we are going to need a lot of basic theory, and theory that we have studied in statistics and theory that we have just studied right now, which is basically the application of these things. So I'll give you a minute to understand this on your own, and then we can start. Now for the examples part, I'll write down the questions first, and then we can solve them. So consider a radar system that uses radio waves to detect aircraft. The system receives a signal, and so understand the problem carefully first. Read it once again when I complete finishing it. When I finish the problem, and then after a while we can start discussing the solutions one by one, because there are multiple parts to this problem as well. So up to this part we are clear, because what we have said is this, and we understand what W is. W is basically a standard normal variable, a normal variable, a normal random variable with mean 0 and variance 1 by 9. Now, that brings question A. So I'll explain the problem again, but let me just write down the questions. There are five such questions. So the first one is write the null hypothesis and the alternate hypothesis in the terms of theta. So that completes the questions, and now let me explain how do we actually do it. So basically, it says that consider a radar system that uses radio waves to detect aircrafts. So there is a radar system that uses the radio waves and it detects aircrafts are present or not. So this how it works is the system first receives a signal, and based on the received signal, it needs to decide whether there is an aircraft present or not. Right now, if X is the received signal, and we already know that if X is W, then there is no aircraft present, and if X is 1 plus W, then there is an aircraft present. Right now, here W is just W belongs is basically a normal random variable with mean 0 and variance 1 upon 9. So that's the probability distribution of W. So W takes values according to which has probabilities according to a normal distribution with mean 0 and value variance 1 by 9. Thus, what we can do is we can write x equals to theta plus W. We're just trying to introduce a parameter, and you would notice that if theta is 0, then x is basically W, which means there is no aircraft present, and if theta is 1, it means there is an aircraft present, and we can write x is 1 and 1 plus W. Now suppose that we define the null hypothesis H naught as no aircraft is present, while the alternative hypothesis H1 as an aircraft is present. Now the questions. Let's go for number 1. Write the null hypothesis and the alternative hypothesis in terms of theta, right? So the simple hypotheses are as follows. Part A, we have that H naught, which is the null hypothesis, it can be written as theta equals to 0. That is, no aircraft is present. Then we have H1. H1 is basically the alternative hypothesis. So let me write down alternative, and this is theta equals to 1. That is, aircraft is present. Okay. Now to decide between H0 and H1, we look at the observed data, obviously, and this observed data tells us if we can differentiate between H0 and H1. That completes part 1. Let's now for B, design a level 0.05 test to decide between H0 and H1. So when we say a 0.05 test, what we actually mean is we are trying to decide, we're trying to make a test which can help us distinguish if to decide between what is true, H0 or H1, what to accept and what to reject, and the level of significance should be 0.05, which should be our helping hand. So to decide between H1 and H0 and H1, we look at the observed data. The observed data is just the random variable x, right? The observed data random variable x under H naught x follows normal distribution with mean 0 and variance 1 by 9, and under H1 what happens, so this is under H naught, right? And under H1 what happens is it follows normal distribution with mean 1 and variance 1 by 9. Why is it so? I'll explain that. Because under H naught W, therefore E of x is equals to E of W, and W is a standard normal variable with mean 0, so this is this, and also variance of x should just be variance of W, which is 1 by 9. Therefore x also follows a normal distribution with mean 0 and variance 1 by n. And under H1 x is 1 plus W, and this means E of x is simply, so the mean is 1, and adding a constant to the variable doesn't change its variance, because variance of x then would be variance of 1 plus w. Therefore x follows normal distribution with mean 1 and variance 1 by 9. So yeah, that's how it works. Now the test. Now what we are saying here is we can suggest the following test where we choose a threshold c, and if the observed value of x is less than c, we can choose h naught. Otherwise, if it is larger than c, we can choose h1. So that's what we are going to do. Now to choose that c, we are going to use our required alpha. So let's see.